Hey everyone, my name's Ross or Soysaw on the Discord, and today I'll be talking about my ErgoHack 6 project called Ergo Tizen. We'll go over the what, the why, and then a bit on implementation and what's next for the project. The goal of Ergo Tizen was to experiment with creating a node that can run in, but not limited to, web-based environments like web browsers and web views. Furthermore, I wanted to run the node on a smart device in order to determine if this was a viable approach for creating a node that runs on a wide variety of devices, utilizing WebView and web-based technologies. This is where the name Tizen comes from. I wanted to run it on a Tizen-based device, which is Samsung devices. Additionally, I wanted to investigate if the node could be compatible not only in web environments, but natively on desktop computers as well, with the same code base and minimal platform specific code required. So why would we want to make a node that's compatible with web technologies? So to clarify some things about the node, firstly, the node doesn't aim to be the fastest or most efficient node. It's aiming to be a node that can be run on a very wide variety of platforms as easily as possible, while keeping the development overhead of targeting many platforms as low as possible. I think that portability and cross-platform challenges are an area that web-compatible nodes could really help with. I think it also opens up some unique use cases with browser-based nodes, such as embedding the node in wallet extensions to provide light node functionality to wallets. This would also help to remove trust on external nodes for wallet users, as they would be running their own light node within the wallet. I think this would also help the overall network security, as there would be more nodes on the network as well as a side effect of this. So how exactly can a web-based node help with portability and cross-compilation challenges? This is a screenshot from the C++ Ethereum Cross project, which is a project from around 2018 that was trying to cross-compile the C++ Ethereum client for cell phones, wearables, and other smart devices. As you can see in this matrix just for cell phones, getting the node to compile and run on all the different devices can take a lot of effort, and ongoing effort as well as new hardware is released. And this is just the first part of the puzzle. After getting the node compiled and running, how do we use it in an actual app that a regular user would want to run? So we need to create bindings in order to create an iOS or Android app for the phones, which adds more development and more complexity. A nice bonus for web-based nodes is that they will be able to integrate very easily with popular web UI frameworks like React, leading to a good cross-platform experience for users. In general, I think that this is an area that will be a big challenge for all node software running on smart devices, which is how do we make something that the average user actually wants to run? I think having a nice UI and UX should assist pretty greatly with that. So how does a web-based node actually work? Nodes generally require low-level functionality like networking that's not available in the typical web environment. So it depends on what platform the node is running in. So for the CLI, it will be using the Deno JavaScript runtime, so it runs natively and it will have access to all the low-level and platform functions directly. A useful property of Deno is that it implements web standard APIs, unlike Node.js, making it really easy to write apps that work both in web and native environments. When running in a browser as a browser extension, it will use a native application component to perform actions on the extension's behalf. This would look similar to how password manager extensions work if you're familiar with that. There's normally a desktop component, like an icon in the system tray, so this would look very similar to that. For my Tizen project, similar to the browser environment, when running the node on Tizen, I used a sidecar application that had access to platform functionality, and that sidecar application performed actions on behalf of the node and proxied any TCP traffic back to the node over WebSockets. For mobile applications, the node would be running in a web view and platform functions would be binded to the web view, allowing the node access to platform specific functions. This is a popular pattern for developing mobile applications today. At the end of the hackathon, I successfully had the node running in a Samsung TV emulator and connecting to peers on testnet. The node only had very basic functionality implemented, establishing a handshake with peers, and I created a dashboard to display information about the peers that it was connecting to and what it was doing. I also had a CLI version of the node running on native desktop computer and cross-compiling for Linux, Mac, and Windows. Additionally, the node was also able to run in a web browser, which is essentially the same as what you're seeing in the video here of the node running in the emulator. So next steps is to continue building out core functionality of the node, with the first major milestone being to get the node doing something useful beyond just handshaking peers and exchanging a few basic peers related messages on the network. Like the reference node client Ergo, so Ergo is the name of the node resulting from this project. Ergo aims to be multi-mode, so the first goal will be to implement light SPV mode, which is a header sync, which then allows for simple payment verification. Ergo is all open source, so feel free to check it out. Thanks everyone for watching, and thanks to the Ergo Foundation, ErgoPad, judges, community, and participants of ErgoHack. I had a great time working on this project, and I'll see you around.